Alrighty, so I'm going to be talking about some issues with memory allocation and why this is like a challenging area. So I'm going to get into some questions of like where does memory get allocated when you ask for it? What are the options in terms of how you can allocate memory? And then what are some of the consequences of asking for memory in a certain way? And I'm also going to talk a bit about pointers and how they can be very useful and also very tricky. And I think I'm going to probably emphasize just a little more of the tricky, just because, well, it should probably be somewhat obvious to you and not too long why pointers are useful. But okay, so yeah, let me see. Can I do it like this? No, this is only forward.
It's like a mouse.
It's a mouse where the, oh, wait. The left button is forward.
Left button goes forward. Right
Yeah.
button right.
Sweet.
Not useful.
Yeah, okay. Right. So here we go.
Do you want a remote?
No, I'm good. All right, so yeah, the question is, sort of broadly speaking, what happens when you declare a variable, right? So if, let's say you write a function and you say, in my function, I'm going to declare this integer myInt, right? What is actually happening sort of underneath the hood? Or if you have in your function an integer pointer and then you ask for a new integer, what's going on there? And so I'm going to tell you just a little bit about how C++ manages variables. Okay, so primitive data in C++, these are things like characters, shorts, which are so characters and shorts, characters you would use to represent, say, a letter or maybe a very small integer. A short is a slightly larger integer. Ints and floats are both 32 bits per each. They take up 4 bytes in memory. These are all primitives here. And then doubles they take up twice as much memory as floats, so they're double the amount of memory. So instead of 32 bits worth of floating point precision, you get 64 bits of floating point precision. And when you allocate a variable, you carve out a little piece of memory that you have in your pool of available memory for representing the contents of that variable. So if you have some function, you can say, I'm going to declare this integer, myInt, and you can initialize it sort of like a constructor list or style to a particular value, say 2. You can also say that you'd like an array of integers. I'm not great with this, so let me try to do that. And you can specify its size, say 4, and then that would give you, and then you're allowed to initialize that array at the time that you allocate it. And so this is a way of initializing 4 integers at once, so that in succession they have values 1, 2, 3, 4, right? And so what that looks like inside of the cloud of available memory is that there's a little bit of space allocated for myInt, and that gets carved out when the program reaches this line. And when the program reaches this line of code, it allocates more space for this array, your myInts, and it sets the value here. So I'm going to use this notation where I've got like boxes, and each box represents the contents of one of the variables, and then I'll have the name of the variable as needed to the right of the box. And so myInt is just this one integer, and myInts is the set of 4. All right, so classes work a lot like, in C++, classes work a lot like primitive data. I'll get to that in just a second. What I want to say first is that they allow you to group data together. Conceptually, because you would think of like, okay, if you've got a car, then it's going to have an engine and a steering wheel, and these would sort of all be part of class car. And it allows you to think about, if I have a car, then what are the components of it? It groups it together for your thought processes. But it also groups data together physically, so that when you allocate an instance of a class, all the data members of that class live near each other in memory. All right, so let's say you've got your class, my class, right? And inside you've got some private data, a float, an integer, and maybe an array of characters. Then if you allocate an instance of my class in, say, a function, then what the cloud of memory looks like is that you would have 3 pieces of memory, three blocks here. So these are all 32 bits, or 4 bytes worth of memory. So the float takes up 4 bytes, and the int takes up 4 bytes, and then these 4 cars would take up also 4 bytes. And then because of the way that you allocated the memory here, you just said you call the default constructor. So it's going to execute this function right here, which doesn't initialize the data. So the contents of memory here is going to be just some garbage. You don't really know what's there. It may be that if you run the program multiple times, you'll get exactly the same garbage. It'll depend on whether you ran other programs in between, because the operating system may have used that piece of memory to run some other, say, like if you ran Emacs in between when you executed your program twice. So this garbage may change from program execution to program initialization, or it may stay the same. It's a little hard to know, but it's definitely garbage. It's not something that has any defined meaning, because what's happened is that memory always has like an assignment to it, and when you carve out and you say, I'm going to make this portion of memory my variables for this class, it just says, okay, that portion of memory is yours, but it doesn't change the contents of memory at that time. So in this example, what you have in these question marks is garbage here. Okay, so that's one of the things that one of the first things to worry about in allocating memory is that allocating memory and initializing memory are distinct things. And you can allocate without initializing. I don't think you can initialize without allocating. That would be weird. Connection lost. Connection found. Nope. Connected.
You allocate memory here?
So the question is, are you allocating memory here? And yeah, so if I execute some func, right, I enter this function, then the first thing that happens is I declare an instance of this class, and that's allocating memory on a certain way, right? It's a special type of allocation. There are 2 that are available. I'll get into that in just a second, but this is definitely an allocation of memory. Okay, so one of the other consequences of the way classes physically group pieces of data together is that if you have a base class, say this one called base class, and it's got some integer private data member named base int, and then you derive a class from it. I'm tempted to edit my slides while I'm presenting, so I would have to actually say that it's deriving from the base class, which I didn't before, but I will now. So I'll say it's going to derive publicly or obically from base class. Sorry. So this derived class derives from base class. And so derived int is going to be the new data member that this class brings to the party. But it also carries with it the data from the base class. And so if you were then to somewhere allocate an instance of the derived class, then when you execute this statement, it will allocate 2 integers, one for the base class and one for the derived class. And so you can think of every time that you have a derived class, you're carrying with it all of the data that comes with the parent class as well. Yeah?
Can you just clarify again, where would you initialize the memory?
Hit the wrong button.
Where are you doing that?
So this is code where you're initializing memory. So when I said DC here before, let's say that this is inside some function, or it could be you can allocate memory inside CC files outside of functions, which is something we strongly discourage, but is legal. And then that sort of is global data at that point. So this could exist just in a CC file. It could be part of main, like the main function. But anytime when you declare a variable, you're allocating memory for that variable.
And then when you initialize it?
So in this example, neither data member is getting initialized.
Okay. Is that when you set DC base in to 3 or something? Or
Yeah, if you set the value, then that's initializing it. Yeah, and you could do that in any number of ways, but I haven't given you any. Like, if you just compiled this code as is, it would work, but it wouldn't do anything. It would be very interesting because it has no public functions to it. You can imagine where you would. have some public functions. Okay, so right, I promised you that there'd be two different forms of memory. There's the stack and there's the heap. So the stack is this linear ordering of variables that are allocated, say, in functions as they are called. So in computer science, a stack is actually a name for a common data structure. If you have you can visualize it as, say, like a stack of trays in a cafeteria, where what you do is you wash a whole bunch of trays and you put them on the stack, and then as students come in, they like pull a tray off the top of the stack, right? And so the next, like every time someone comes by through the cafeteria line, the next tray that they get is the top one on the stack. It has this funny phrase, this LIFO data structure, which means last in, first out. And so that applies, say, in the way the way memory is allocated for function calls. Like if you have a local variable for a function, when the function exits, then it pops the data members off the stack. It sort of destroys them. They go out of scope. They cease to be allocated variables. And then if you have a function that calls a function, then when that called function exits, its data members get pulled off the stack because they were the last allocated. And when the first function leaves, it exits, then its data members get pulled off. So it's like as if someone's putting more trays on the stack, and then you pull off the ones in the order that they arrive. In contrast, the heap is like you can think of it as like a disordered region of memory. So you have 4 gigs of memory, and they're not all part of the stack. The other way you get memory is on a heap. It is ordered, and it's just not intuitively ordered. So if you ask for 2 sequential new requests, so you allocate 2 integers in a row with the new statement, then you won't necessarily get or have those 2 integers live next to each other. Like there won't be a physical proximity for them in memory. Right. So yeah, in order to get memory on the heap, you ask for new, and then new will return you a pointer, the address for that piece of memory. And then when you say I'm done with this piece of memory, you have to say delete, and that will give that piece of memory back to the operating system, back to C++. There are underlying libraries that control how the heap behaves. Yeah, there's the stack. Okay, so let me go into some detail on the way the stack works. All right, so here's 2 functions, myfunc, and then this second function, swap. So swap first is going to take the reference to 2 integers, declares a local variable named temp. It assigns temp the value a. Then it overwrites the contents of a with the value of b, and it overwrites b with temp. Sorry, I have to edit my slides again. You'd hope that I knew how to write a swap algorithm by now. Sorry. Okay. Excellent. So let's say that you're calling myfunc from somewhere, right? So it's going to allocate 2 variables, right? 5 and 7, and then inside this function, it's going to call swap. And let's see what happens here. Okay, so at this point in the function, it's allocated 5 and 7. And so I've depicted the variables here, 5, and their contents are 5 and 7. Their names are 5 and 7. And I'm actually giving you the address, like the physical location in memory where these 2 variables live at the time that this function arrives, right? So this is the stack. They're going to be allocated right next to each other because I didn't use new in order to allocate them. And the stack sort of is going to grow downwards. All right. So I'm going to call this function swap. And I'm going to enter that function. And what happens is a fair amount of data gets put onto the stack. What first happens is some data is put on the stack for calling convention data. So this is a way in which subroutines call each other and allows for some interoperability between languages. I'm going to have to tell you exactly what data is here, except I'll tell you that it's really important that like swap can be called from anywhere. In order for it to figure out when it exits that it needs to go back from where it was called from, it needs to put some data. These are the breadcrumbs that will help it get back home. All right, so swap is going to put some things on the stack. The first is a reference to A. So there's the formal parameter A that's put on the stack, and its contents is going to be the address of A right here. So it's a reference is a pointer. As far as the machine cares, for our purposes, they're slightly different. B is also allocated on the stack, and its address is also in the contents of the variable, which is here. Sorry, has everyone seen hex before? Maybe I should say what this is. So this is a way of referring to just a big number where you represent, so it's hex, which means it's short for hexadecimal, or 16. So it's got 16 different numbers as opposed to like in binary where you have 2, or in radix 10, like canonical Arabic numbering, where once you get to 10, then you go, or once you get to 9, then you go to 10. It's the same thing, except that once you get to 9, you go to A, and then to B and C and D and E and F. And then once you get to F, then you go to 1, 0, right? And that's now 16. Okay, so anytime you see, so OX just means this is hex, and this means the address that's represented in hex. So you'll see letters between A and F in hex characters. And you likely run, if you print the address of anything memory, you will see these symbols here. And it looks kind of daunting, but it is actually sensical in some way. Okay, so, and the last thing that's going to be allocated we're back here in swap. The last thing that gets allocated on the stack is this variable temp, and you initialize temp with the value in A. So what happens is that this pointer gets dereferenced, this reference, its value is obtained, and the value of A is put into temp. All right, and then what happens next? So you assign a value to, you assign the value B to A, and the way the reference works is it actually changes this data up here, right? A stays the same kind of, its value on the stack remains the same because it's still pointing to the same thing, but it's operating as if it's an actual, like an integer itself, all right? And then B, sorry, the animation, I'm going to have to update my slides. It should be assigning the value temp, and so it's going to overwrite the contents of B, which is up here at this address. So now I've swapped the contents of 5 and 7. Yeah?
So the in function to dereference that pointer, is that, like how did you, I don't...
So what's going on here is that it references syntactically behave like variables, but under the hood are pointers. So even though it says, you know, A is getting this value, what's really going on is not this thing, but whatever A is a reference to, which in this case is 5. So 5 is A, and 7 is B, right?
But in swap, you're assigning A and B. A is the pointer, right? It's a memory location.
Yeah. And so because it's a reference, the syntax this is if this were an int pointer, then it would be star A equals star B. But it's a reference, and so the syntax is slightly different. So you can think of it as if it were a variable itself, but it's actually it's a reference to a variable. So that's one way in which plus is a little, right? Because pointers and references are in many ways the same and in many ways different.
Okay.
Yeah.
Might be really quick, like what's the difference between initializing something with like in brackets or with an equal sign? What's their difference?
So this is a declaration. So I say int temp. So this is a variable declaration, which you're probably familiar with. And then this is basically a constructor for an integer. And you give it one parameter to this constructor, which is the value that's in A. So it'll be initialized with the value 5. All right. And now this is actually assignment. It's not allocating. It's not declaring A. A already exists at this point. And you're just assigning the value that's in B to the thing that A points to. Yeah.
What's so confusing to me though is that you passed 2 pointers then, right? A
Uh-huh.
and B. So how does temp know about A? Should it only know about this pointer, right?
So let's see. So A is the formal parameter,
Right.
and 5 is the actual parameter. And so I pass 5 and 7 as actual parameters to swap, and it allocates formal parameters on the stack for these two.
Right.
And so this is A,
Uh-huh.
and then this is B. And so it knows it's going to have pointers to both of these two,
Right.
to the variable 5 and the variable 7.
Okay.
Did that answer your question?
Yeah, but then when it has, how do you, but it seems like you passed the pointer, so how do you know, how does it know about the contents of the?
Because of the nature of references, it says that, so reference, like this syntax means dereference this pointer and assign it a value.
Okay.
And then this syntax means get the value out of this pointer. Right? It looks like a variable,
Right.
but it's actually a pointer. But it looks like a variable. It's a little tricky. Yeah. So this could be rewritten so that it's int star A and int star B. And then in here, I wouldn't pass it 5 and 7. I'd pass ampersand 5 and ampersand 7 to get the addresses of each. And then the stack would look the same. Right? And then this line of code would be star A equals star B. I guess I skipped this one, so this would be int temp is star A. And then this would be star B equals star temp. Remember that I screwed up this 3-line function. So that this should be a temp here as opposed to A. All right. And so then it would have like pointers to each of these two variables, and it'd be modifying these two variables. Like modifying the contents of these two variables, right? And so, yeah, I hope that was a little more clear.
Okay.
All right. Okay, so right after this function exits, so there's an implicit return at the end of each function. Then it jumps back up here using this data that was pushed on the stack when you called this function, and then all of these variables get deallocated. Right? This piece of memory is no longer reserved by the program for its execution, right? And so that happens like, oops, wrong direction. So that kind of like pops it off the stack. So remember, the stack was growing down, and then this function exited, and so this memory gets reclaimed. So if there were another function call down afterwards, then it could reuse this section of memory for the new function.
Is there any limit for the size of the stack?
There is, but yeah, because you can only grow linearly until you run up against something else. But you can configure that with your build command, and I think our stack is big enough for most things. We have like, for instance, every time you call a recursive function, you put more data on the stack every time you descend into it, and we can refold the ribosome. So our stack must be big enough to step through each of the atoms in the ribosome and update their coordinates. So I think you're probably unlikely to hit an error where you've run out of stack. Backwards, forwards. Okay, so I just told you about that, but let me show you what that be. So this is a recursive function. So if this is my program int main that I call countdown 3, can I give you guys like 30 seconds to stare at this code here and in your heads figure out what's going to be the output, and then I'll ask for you all to say it at once. Okay, let's hear it. On a count of 3. 1, 2, 3. Sweet. All right. So what's going on here? So countdown is called, right? It has initially the value 3 is passed in as the formal parameter, right? So in memory, there's actually probably stuff up here as well, but I didn't show it. But this will be, say, the first variable that's put on the stack. All right. So that's the parameter x. The formal parameter x, and it's going to have this value 3. right? And so the first thing that happens is that 3 is output, right? And then it executes this. So if x is less than 1, or if x is greater than 1, then call countdown again, but with this value of x minus 1. So what happens here is that then we're going to put on some data on the stack so that we have our breadcrumb trail to get back to where we came from. And then we allocate yet another copy of x, the formal parameter here, with now the value of 2. We output 2. We go down to x greater than 1. This is true, and so we're going to call countdown one final time, the value of 1. All right, so it's going to put some data on the stack for our breadcrumb trail to get back home, and then the value of x will be, or another copy of x with the formal parameter x with the value 1, right? And at this point, you're not going to recurse any further, and instead you're going to yell blast off. As this exits, then this function ends for when x was 1, right? And it's going to return to here when x was 2, and then execute the rest of this, which is nothing. And so it's going to pop this data off the stack as well. And then finally, it's going to return to this position when x was 3, and then it's going to finish and it's going to pop off the stack.
So why doesn't it want to be 3 blast off?
Oh, because it output 3 before it descended into that. So it says 3, and then it executes it for 2, and it says 2, executes it for 1, and it says 1, and then finally blast off. Yeah.
Maybe slightly outside the scope of this, but where does like the function pointer, like where is that in the stack? Because it needs to know like where that is to even start.
So in order to call this function, that's sort of so I won't get into it because or I didn't plan to get into it. There are 2 different places where you have memory. There's instruction memory, and then there's like data memory, and those are kept separate.
Oh, okay.
And so you don't even have the choice to like mess up.
Okay.
Like you can do all kinds of awful things to data memory, but you don't. The programming language doesn't really let you mess up instruction memory. So yeah, that's basically when this is compiled. The compiler, or when it's linked, it's going to figure out the address for this function, and then it's going to jump to that address. Yeah. Okay. All right. So like I said, you can do awful things if you want to. So this is an example where we're going to corrupt the stack. All right. And the stack is it's data memory. So like I said, I mean you have the power to do awful things to it. And so here's a way, a perfectly legal program. C++ will happily compile this for you. It will execute no warnings, right? Where you end up with a seg fault quite quickly. All right. So I got this function test corrupt, and it's going to iterate and call this function corrupt with value 5 and this value I, the loop counter, and it's going to do it 3 times. All right. And so corrupt is going to take 2 values, val and offset. Right? It allocates a pointer. An integer pointer, PDR, and gives it the address of offset. And then it's going to change pointer. Right? So this is pointer arithmetic logic here, where I'm going to increment pointer by the value of offset. And then I'm going to dereference this pointer. So I'm going to go to that address, and I'm going to change the contents of that address by val, and then output what just happened. So you can, later when you're feeling like you'd really like to see what's going on, you can take this code snippet and you can put it into a little program and run it, and it will crash. So what happens? So I is this variable that's going to get allocated in this for loop, right? And I'm going to call this function corrupt 5 with I, right? So the first thing is that I'm going to allocate some C calling convention data. This is my breadcrumbs. And I'll set the value val to 5 and offset to 0. And then at this line, I've allocated pointer and initialized pointer with the address of offset. So PDR is pointing at this address, and there's the value there. So then I increment pointer by offset, it's 0, so it stays put. Then I'm going to dereference this value and increment it by 5, which will change the offset now to 5. And then I'll output it. And so the first output is 5. All right. Second time around, I say test corrupt, and I'm going to have the value of I is going to be 1 now, all right, because I've gone once through this for loop. All right, so I'll come up here. I've got my C calling convention data. I've got 5 is the value of my val, and 1 is the value for offset. And then I initialize pointer with the address of offset. So this is the address for offset. I change pointer by offset. So now it's going to point at val, right? So val and offset are right next to each other in memory. So when I increment my pointer by 1, in pointer arithmetic, it's incremented by the size of the thing that it's pointing at. So integers are 4 bytes. So I went from F0 to F4. Is the next integer block in memory, right? And then I can change the value in what's pointed to at val by the value in val, which is kind of funny, but you can do that. And then output it. So the next output will be 10. Right? And then the last iteration through this, I'm going to, again, put 5 and now I is 2 on the stack for val and offset. I'll initialize this pointer to point at offset. I'm going to change this pointer. So now it's going to point up here. And this is like the forbidden zone of memory, right? And I'm going to change it. And I've now corrupted it. And I've kind of ruined my breadcrumbs home. And then, sorry. So at that point, it's corrupt. If you look at the output, it's going to be different for each machine. But when I ran it, it was some very large, like 10 million something. It was incomprehensible. But it's still interpreting this as an integer, right? Even though it's right, just some weird piece of memory here. Who knows what this is? It's actually a pointer. But so it's referencing some other location in memory. And when this function tries to leave, it suddenly can't find its way back home, and so you get a seg fault, right? So that's
how do I know you were reaching into the forbidden zone?
How did I know? Oh, well, so
I mean, how would you have known that?
I guess you familiarize yourself with stack corruption, how it would work, and then you come up with an example such that you can corrupt the stack. It's definitely like after, so when this is, so offset in this case is 2, right? And I've got 2 things that are allocated. And so after so if I hop back from offset, then when I hop back one more, it's going to be some of this C calling convention data. Right. Okay, so the stack corruption takeaway. Maybe I could mention this, which is that this is how you hack a computer, which is that you figure out how to corrupt the stack in a reasonably intelligent way. The function exits that, so you call function, corrupt the stack, and then it tries to go use its breadcrumbs to find out which code to execute next. You insert an address in memory where your new program lives, and then the program just starts executing that stuff. And that's where it starts sending spam or deleting the contents of your hard drive or signing you up for Hotmail accounts or something. Anyways, so stack corruption is kind of something that lots of security people spend a lot of time worrying about. Okay, so stack corruption. So pointers give you the freedom to do lots of stupid things. So we do want you to be careful with pointers. You want to be careful about pointing a pointer at a variable on the stack. It's perfectly legal to do it. It doesn't necessarily mean it's a good idea to do it. References are quite a bit more safe because the difference is that even though under the hood they are pointers, you cannot change the programming language doesn't give you the power to change your reference. You can't change where it's pointing to. You can only change what it's pointing at. And so if you have a way of using reference instead of a pointer, we highly recommend it. So if you have 2 stack variables and you want to have their contents modified in a function, you can do that with. If you have 2 stack variables and you want to change one of them, but you're not sure until runtime which of the 2 you want to change, instead of creating a pointer and pointing it to one of the 2, you can use the ternary operator, which looks like this, and it's really a question mark and a colon. So you could so this is how it would look like. If I have two integers, int1 and int2, and I wanted to create an int reference, then I could say, is int1 greater than int2? Maybe that's a condition by which I want to decide which of the two I want to point at. Then if so, give me int1. If this is false, then give me int2. So this is an if-then-else construct in other language, where you have an if clause, a then clause, and an else clause. So it's a little function almost, but where you haven't gone to the trouble of actually declaring a function. And then the biggest one is, yeah, maybe there are definitely some times where you want to create a pointer to something on the stack, but be wary of incrementing a pointer, right? There are few cases in which you need to increment a pointer, and if you don't know exactly why you would want to increment a pointer, you don't want to do it. Okay, so that concludes what I was going to talk about with the stack. The other half of memory allocation is the heap. And so I was going to walk through a couple examples where I talk about allocating memory on the heap, using data structures that allocate memory on the heap, and then some of the problems that you can have working on the heap. All right, so so you use the new command to allocate memory on the heap. Use the delete command to deallocate memory, and then there's no sense, as I said before, when you say new twice, there's no sense in which the two pieces of data would be allocated next to each other in memory. You're not going to get that sort of convenience in terms of, let's say you wanted to do some pointer arithmetic and switch between the two. You couldn't do that with data allocated on the heap.
So is it safer to use instead of stack?
For certain things. Each has their own drawback. If you're not doing pointer manipulation, stack is perfectly safe, right? If you're not pointing pointers and then modifying their like saying, okay, I want pointer -3, then you're fine with the stack. The heap has its own set of challenges associated with it, and you have to use one of the two. So it's good to just know what are the drawbacks and the advantages of each. So one thing about the heap is that it's much slower to allocate memory on the heap and much slower to deallocate memory off of it once you're done with it. So if you have a function, for instance, and you have a choice between handing that function a string or a string reference, it's a lot faster to hand the reference because the reference gets allocated on the stack. But when you create a new string under the hood, it's going to allocate space now for that string and copy its contents. It's going to use new and delete inside that. Inside the construction of that string, which is why you can slow things down quite a bit if you pass the wrong set of, or if you create functions that have the wrong set of parameters. Okay, so the three examples that I'm going to show you are, say, allocating an object on the heap and deallocating it, allocating and deallocating an array on the heap, and then I'm going to show you what it'd be like to write a linked list on the heap, which is maybe an exercise that not everyone's done before. How am I doing on time, out of curiosity?
It's 2:20 or so, or 2:20.
Okay. Okay, so let's say I've got this class, my class. All right, it's got two data members, my int and my float, and I initialize them in my default constructor, so that a constructor that takes no arguments. And I allocate an instance of that class. So I create a pointer of type my class pointer, and set that to null, to 0, and then use new to create an instance of my class. So this is going to call the default constructor, and it's going to initialize the data like this. And at some point when I'm done with my class, then I'm going to delete the contents. I'm going to use the delete function with giving it the my pointer. All right, so when I say new my class, new returns an address, and so it's going to change the contents of MC Peter. And then it also is going to carve out a region of the heap. So data was allocated somewhere over here somewhere. This is the stack, let's say. And it's going to initialize my int to a value of 0 and my float to a value of 1. All right. And this is a pointer in the sense that you can think of it as pointing to a region of memory. And I've talked about pointers a little bit already, but it's holding an address. And so it's always kind of pointing somewhere. because it's always an address for something. And then in this case, it's holding the address for this thing that we've just allocated. All right, and then what happens when I call delete? Well, I deallocate this section of memory off the heap, right? Delete has not changed MC pointer, right? It's still got the value that it did before, and in some ways it's still pointing right at here. It's just that this is now region of memory that's accessible to C++, to the operating system to allocate other stuff in.
Has the information there been deleted, or it's still there just?
And then the contents of this haven't necessarily been changed. They might have been changed. They might not. So the heap, like I said, it was a non-intuitively ordered data structure. It actually has lots of pointers inside itself. So there may be something that points at this piece of memory. It may point to some other piece of memory, and C++ is going to manage the construction of the heap. And you can do awful things on the heap like you can on the stack, where you corrupt your heap, and then the next time you call new, it can't find its way through memory to give you that piece of data that you requested, and it crashes then. And the problem with heap corruption bugs is that they crash when you say new, but you corrupted the heap a long time ago. And so you have to figure out when you wrote to that piece of memory that you shouldn't have. Yeah, it's the worst kind. And for that you need, they're actually, GDB has this really awesome hardware watch point thing where you can give the address that you know gets corrupted and figure out what line of code is corrupting at that address. It's really slow, but it's way faster than reading your code and trying to figure out where you messed up in coding. And that's how I have debugged all my heap corruptions in the past. Okay, so right, so deleting MC pointer hasn't changed this. It may not have changed the contents of memory. If you were to insert another line of code here down here, where you allocate another MC pointer to, and then initialize it with a new my class, it's possible that you'll allocate this piece of the second piece of data in the same place you did before, and now you've got this pointer that's pointing to something that it shouldn't really belong to, or doesn't really have ownership of, and this one that's pointing there where you've just allocated it. And so that kind of scenario is where this pointer has something that it ought not to have is called a dangling reference. We'll cover that a little bit more later. Right, so let's say you're back here and you've deleted MC pointer. One of the safer things to do is to, immediately after you've deleted the contents of memory, change the pointer so that it's null, in which case it'll stop pointing at this location of memory. And if you were to do something later where you set the value of MC pointer to, or tried to dereference MC pointer, then you'd get a crisp segmentation fault as opposed to some sort of murky writing to a piece of memory that you don't have ownership of issue. Okay, so the second example that I was going to show was allocating an array on a stack. So arrays and pointers are interchangeable, which is a little cool and a little scary. So you have a pointer, and you declare this int array pointer. So that'll give you, say, a location. Oh, sorry, a piece of memory that's for int array. And remember, when you allocate a piece of memory, you haven't set its value, you haven't initialized it. And so at this point in time, it's holding garbage. So it's pointing to somewhere, maybe off the screen, maybe in another room or something, right? Some piece of memory that it shouldn't belong to. And if you were to do anything with this pointer, as soon as you've declared it, C++ would say that's fine, but your program would crash. All right, so in the next line, let's say you're going to say int array equals new int, and then you give it this value n. So if n were, say, 4, then you would allocate a block of four integers in memory. And so they would be right next to each other. So when you allocate this, with this style, you actually get sort of this data locality property where all of your data is right next to each other. Right, and then int array would be assigned to the location, the beginning of this array in memory. And then when you're done with this array, then you say delete and use these brackets to say that I'm deleting an array. And then it would delete all of this contents of memory.
The pointer is still there.
Yeah. And so it continues to point to it even though it's now deallocated that section of memory.
How does it know how long the array is?
I wish I knew that. It's either magic, or there's something about when you allocate with new, it figures out how, like if it's an array, then how long it is, so that as it's trying to get, I'm not really sure. Yeah.
Could you go back to the previous slide, please?
Sure.
So, can you delete multidimensional arrays using a single delete?
So if you had, instead of an int pointer, an int pointer pointer, so you allocate an array of int pointers here. So it's say new int star, and then you give the brackets. And then you would iterate across each of the elements from I equals 0 to n, or less than n, and then say new int, and then of size n, right? Then each one of these would be a pointer to a different place in memory, right? And then when you delete this int array pointer pointer, it deletes this array and none of the others, right? So you would have to first go through every element of this array and call delete this guy, delete that guy, delete that guy, and then delete that guy, before you could then delete the int pointer pointer array. Sure. Okay, so how would you, so maybe people have used standard list in C++, or maybe you've are old school enough that you've implemented your own linked list at some point. How would you go that? You've done it? Awesome. I started with Pascal, and so every time you wanted a list, like there are no templates in Pascal, so you had to create a different list for everything that you wanted in your list. So in this example, I'm going to show you what an int linked list looks like, and it consists of two classes, a linked node and a linked list. And I want this linked list to have these sets of functionality. So adding a new link to the beginning of the list should be possible. You should be able to delete the first element in the list. You should be able to search for an element of a list to find the first element of a list. You could maybe want to find and delete an element of a list. And maybe you want to, I don't think I've gone through the code that's necessary for this, but you would also want it to clean up after itself, so that you could say, delete everything, and it would just delete everything.
How is it different from a vector?
A vector gives you a contiguous block of memory. And when you say you have a vector with like 5 elements, and you say, okay, I want to add a 6th element to it, then it has to allocate another vector of size 6, and then copy each element out of the original vector to the new one, and then delete the old one. So when you keep pushing back into a vector, it's a somewhat slow operation. If you want to, we can later talk about how you can make that. Like if you know ahead of time that you want 20 elements in your vector, and you want to use pushback as opposed to assigning into there's a reserve function that you can use to say, make sure that when you allocate the first vector, that it has 20 elements, so I can keep pushing back into it.
Can you just resize it, like right before, like so suppose you like suddenly realize you need 20, and you start at 5. Could you resize to 20, and then when you call pushback, it wouldn't do the resize each time?
If you resize,
yeah.
So this is a technical detail of standard vector, and it's going to take me over time, but it's fun. So a vector is like, so you have, let's say you got 3 pieces of memory, and it's going to point off here. So so this is M start, M end, and M memory end. Right, and so these are pointers, and then here's my array. Okay, let's say it's a vector of ints. So this pointer is going to point at the beginning of the array. And then this pointer says to the end of what's been pushed into so far. And this one says end of what's been allocated. So if I have like, so let's say I've got 4 elements in my array so far, and I want to push back into this array, but I've resized it, I've reserved it so that there are 20 elements. Then it just updates mEnd so that it can go here. So that would happen after you call push 5. Right? But if you resize the array, so when you call resize, so let's say it was 5 to start, and then you call resize, and it's going to be 20. So let's say it looks like this to begin with. Yeah. and memory end. Okay, so maybe it had 5 elements to start and was size 10, and then you say, okay, now I want it to be size 20, so I resize it. The thing that it does is that it is going to allocate a new block of memory. So this is the new block of memory. And then it's going to say that everything is over there, right? And so when you push back into this vector, like so it'll also copy, so this is 1, 2, and 3. I told you there were 5 elements before. So it'll copy those 3 things down here, and then it'll fill in the values for all the rest of them with the default constructed value for that thing. So if you have an array of classes, then you'll get the default constructor for those. But an integer doesn't have a default constructor, so this is just nothing but garbage. And then when you push back at that point, you actually are going to allocate a third array, which is larger. It actually doubles it each time you do it. So it would go off the end of the line here and then wrap around on the next thing. And it would copy all of the old values here, and then it would put your new value at the first thing there. So you would have the first 5 and then garbage and then your 21st value that you pushed into it there. So that's sort of the difference between reserve and resize, is that you can't just push back into something that you've resized.
Okay. Yeah. Okay. I think I got confused. I meant resize and then overload the array like to use the bracket.
Yeah.
Okay.
Sure.
You can do it that way though, right?
Yeah.
So, okay.
Yeah. You can resize, and then that would sort of avoid the.
Yeah.
I mean, let's see. So there's this logarithmic cost to it because when you hit the end of it, it says, well, I think you're probably going to keep growing it, and it's probably going to be about twice as large as it is now. And so, so you can, if you start allocating with 1, then you would have like as you went up to 32 elements, you would have 5 of those resize operations. So it's again, there's a logarithmic scaling to it as opposed to a quadratic scale. Or you don't resize the thing every time you push back into it again, because it has this capacity to have more memory than what it's currently using. Okay, so that's an arcane detail size. There we go. Chrome.
You have to change the screen. Or like flip to a different.
Did I? Okay, so let's. I don't know where it is, but.
Yeah, it's like all the, you know, how you have the multiple.
I think these are mirrored displays. I don't know whether maybe. It's weird. Okay, so let me scroll down to where that was. Okay, so past here. Okay, so all right, so let's look at what the data's going to be like. So I'm going to have 2 classes, a linked node, and then in just a moment a linked list. But let's talk about the linked node first. So it's going to have a next pointer, so it can point to the next object in memory, and it's going to have the value. So this is the payload. This is the integer that I'm carrying around in each one of these nodes. And so you can imagine this default constructor where you initialize it with the value and set this value to be some input value, and then the next pointer to be null. And then here's getters and accessors. Or I'm sorry, getters are accessors for the value and for the next pointer. And then for setters and mutators, the value and the next pointer. So that when you allocate a linked list, then it's going to have a pointer to the first element in the list as its data member, and then it's going to have these operations. We'll go through what these operations are like. Okay, so if you want to append an element to the beginning of the list, all right, so you would take a list that looked like this, say it's got 4 values in it, 3, 14, 12, and negative 23, and then you're going to modify the list so that it's going to point to this new node, 100, which has this payload of 100, And then that node's going to point to the rest of the pointers in the list. So what would that look like? So this is the function push. All right, so you're going to declare a pointer to this new element and allocate it with new. All right, you say new element dot next is going to be the current head pointer for the node. So in this case, there's a pointer to 3, and you're going to copy that pointer to your new node, right? And then you're going to say the new head pointer is the new element. So that list now points at that new element.
But aren't you going to be writing, what about 3?
3, so in this picture, 3 is got its value and it's got its pointer, and that's the same before and after.
But didn't you copy 3's pointer and then you put 100?
What did I do? I said I'm going to create a new element, and it's going to have this value val. All right, so initially it's going to set its payload to val, which is 100, and then its pointer to null. Right? And then I'm going to say the next value for this new element should be where 3 is. So I'm going to, head already points at 3, so I'm going to assign this element the value head. And then I'm going to set head now to stop pointing at 3 and start pointing at this new element.
Where is head?
Head is a data member of the linked list. So it points to the first node in this list.
Oh, okay.
Cool. All right, so what about deleting the first element of the list? So if you called list.pop, if you tried to get rid of the first element of the list, so it was 100 and now you want to set it to 3. So what happens? It's sort of the opposite. So first you check to make sure that head points at something, and then you say head equals head next. So you reset your pointer to the thing that it was pointing to before. So head next would be 3, and then you set the head pointer to point at 3. So you'd make this transition. Does anybody see a problem with this code?
Then what 100 is just sitting there, right?
Yeah, it's kind of just stayed put. So you modified head so it's pointing at where 3 is, but you haven't done anything with 100. So so the way that you have to deal with this is that first you need to keep a copy of that. So you need a temp to point at head. Right? You're going to change head so that it's now going to point at 3. Right? So you got this that's pointing at 100. And then you're going to delete the temp pointer. You're going to delete 100.
With that, say I forget deleting the node equals 100. It shouldn't interrupt with my program, or does it within memory, right?
Yes.
That memory is still allocated, but it's not going to interfere with the way my program is running.
Unless, of course, you run out of memory,
Yeah.
at which case it interferes very severely with your program.
That actually comes to that.
Uh-huh. It comes to that more often than you would expect. Yeah. So it's bad practice in general to not delete memory that you created. So this is so this kind of bug is known as a memory leak. Yeah, that's what it's called. Sorry, I was getting the other bug in my head, the dangling reference bug. Right, and if you use pop often enough, this will consume all of the memory that you have on your system, and it'll I guess in 2 different ways it could proceed. The first is that it'll consume all available memory and then spill over to disk, at which point your program starts running very slowly and you're not sure why, but you're patient. And so you wait for a very long time as it allocates all of virtual memory, and then it runs out of virtual memory, at which point it crashes, and you say, well, I shouldn't have even waited.
Yeah, but if say I run this and I forget to leave my memory, when I finish running the function, shouldn't the operating system, the garbage collector, should clean up the memory, the unused memory?
You're thinking of Java.
Yeah.
Yeah, there's no garbage collection in C++.
All right. So
Yeah.
All right.
So in C++, you have to manage your memory yourself. It has advantages and disadvantages. I can't go into the difference between the two, though I'd love to. I love that conversation. Okay, so right. So how would you find a node? So let's say I'm going to declare this Boolean, and I want to know whether 12 is contained inside this list. So I'm going to ask list. Say I've got an instance of the class. I've named it list, and I've constructed it in this way, and I want to find 12 to see if it's in there. So you imagine that proceeding like this. First, I look at the first node, and I look at the second node, third node, and I found it, and so I'll return true. I'll say, yes, 12 is contained here. So how does that work? Okay, so let's consider this in two parts. The function find itself, and then this function, which is going to do the finding. And the easiest way to do it is to recurse. So, so find node, you give it a node, and you ask, does that node have this value? And so the logic could be, if node is not the null pointer, or if node is the null pointer, then no, we're done. We've gotten to the end of the list, and we didn't find the value, so the list doesn't contain this pointer. But if it's not null, then ask, does it have the value that I'm looking for? And if it does, then go ahead and return true. If not, then recurse on the next pointer and give it the same value. So that would walk down through memory and get to each of the values until it got to 12. Okay, so how would you delete the first instance of an integer in the list? Like when you want to delete 12 here, you would want to walk until you get to 12, and then you want to deallocate 12, and then change this pointer so that it points at negative 23. So you want to update this so it's still a reasonable description of the list in memory. It would be a shame if you lost this element of the list, or if you didn't deallocate 12. Okay, so let's try it this way. So again, I'm going to break it into two parts, delete first, and then the second part, which is going to find the node that's of a particular value. So, so first I'm going to ask, do I have the null pointer? And if so, return null. Otherwise, if I don't have the null pointer, then ask, do I have the value I'm looking for, and return the node. And if not, then recurse on the next item and get val. All right, so I'll call this function. I'll return the node 4. And then if that's not the null pointer, then I'm going to go ahead and delete that node. Does anybody see a problem with this? Which one?
The previous one.
Right. So in this example, the previous one is going to be 14, and it's going to point at 12, even though you've deleted 12. So we haven't updated this 14 to point at the next guy, and you've left it sort of pointing in the wrong place. The animation is going to give that away because it's not grouped. But yeah, so you created this state where you're pointing at a deallocated region of memory, and you're not pointing at this element that should still be part of the list. All right, so let's correct that by trying another one where I retrieve the previous node. So I'm going to look ahead from the node that I'm at. So if I want 12, then this one should give me the node at 14, right? I want to be able to get to this guy so I can change him. And so this will say, if I've got the null pointer, then return null. If I've got, then if my value is the one I'm looking for, then return. So I'm going to give 2 pointers, one to prev and one to node. I'll look at node, and then I'll return prev if I'm the sought node. So if I'm the 12th the node that has 12, then I'll return the pointer to previous, which has 12. And how do I call that? Well, I set it up so that retrieve node passes itself as previous, and its next pointer as the one as node, right? And then I continue looking for val. Yeah?
I'm not familiar with that syntax for node val.
So this arrow?
Yeah, the arrow.
So this is the dereference operator. So when you want to get, you have a pointer to an object, and you want to call a function of that object, then you use this arrow in order to say, dereference this pointer, and then call that function on that object.
Usually the star is the dereference.
Right, but the syntax would be a little different. You could say, just say here, where are we on time?
It's 2:45.
Okay, so this is going to go very quickly. So if you said, so you got my class pointer, and you want to call some func, right? So you could do it Peter up arrow func, or you could say you dereference the pointer, and then you use the regular function call, like the thing here, dot func. And I'm pretty sure you have to do it like this, because I think this operator takes precedence over that operator. So you have to have all these extra parentheses. And so the arrow saves you a few keystrokes.
Called syntactic sugar. It just means
Yeah. Okay, so in this case, right now I'll have the pointer to 14, and so when they get that pointer back, then I want to make sure it's not null, and if it's not null, then I'll change its next pointer to be the next pointer of the node, and then I'll delete the node. And that would work fine if I didn't have the problem of deleting the first element of the list where there wouldn't be a prev node. So I forgot to tell you that I gave 2 copies of the head pointer when I got started. Okay, so I got a special case that, which looks like this. I'm going to animate slowly through this. All right, where now if prev node is head, then I've got to do something special. Otherwise, I'm going to proceed as usual. And I'll let you guys look at this offline. Okay, so right, there were 2 big issues with allocating data on a heap. The problem of memory leaks and the problem of dangling references. Right, and I think we've covered most of those. I can tell you this is an extra example of a function that leaks. It should look a little familiar, where you allocate an array of size n, and then you iterate across that array, computing the Fibonacci values, and then return the last element of the array. And that's the right answer it'll give you the right answer for Fibonacci, but it won't deallocate the fib array as it leaves, and so that's gonna leak a substantial amount of memory every time you call it. So dangling references are also a problem. So you can imagine 2 movers in Rosetta that share a score function pointer, and then say they're both set up to point at this one, and then maybe one of them decides to delete the pointer, or maybe somebody else decides to delete the pointer. Then it's not clear what would happen when the pack rotamers mover tried to use that score function in its apply method, right? Because the score function has been deallocated, right? So this is a dangling reference, and it's a problem. Right? So the point is that as a lead into a description of smart pointers can help you get over both of these issues. So in Java you have garbage collection, which is a lot like this, but just a little tiny bit better, if quite a bit slower. But it solves this dangling reference and memory leak problems. And the way it does so is that for each object that you have, you keep track of how many pointers point to it, which is a really simple idea. So you have this reference count, and when you create the object, you say point 1 pointer at it, and then its reference count will be 1. And if you pointed a second pointer at it, its pointer would be 2. And so long as someone's pointing at it, the object says, well, I'm still being used, so I should not be deleted. Then you say point your second pointer away from the object. You decrement the reference count from 2 to 1. You delete, or you point the second pointer, the first pointer, I guess the second in my example, away from the object, and you decrement its reference count from 1 now to 0, and then magic occurs. The object says, wait a second, I was pointed to before, and I used that pointing to know that I was still important, and now no one's pointing at me, I must be done. And it deletes itself. And so that's how smart pointers work. In Rosetta, we use this class called reference count, and we have that as our base class for almost everything that we have. So if you declare a new class, my class, then you say it derives publicly from, and it's namespaced here. So this is the utility namespace, and this : means in that namespace. And then there's a pointer namespace that's in the utility namespace. And you use : to say in that namespace, and then the class name is reference count. All right? And so you would say my int is one of the private data members. And the way this works is that the reference count is actually stored with the variable. So that if you allocate an instance of my class, then you would have this bit of data allocated for it. So my int you know about. Count is actually a data member of the reference count class. And this is the vtable pointer that I'm not going to talk about, but is there. And maybe I should say that when you derive from reference count, you have now a virtual class, and so its destructors are now virtual. But I won't delve into that any more than what I just did. Okay, so what we do is we have all these type defs around. So there's a sister class, which is the utility pointer, namespace, and then the class's owning pointer, and it's templated on the name of your class. And so you would say my class and then OP. That's an owning pointer to your class. And when you construct an instance of your class with new, then you put that, the address that's returned by this by the new command into an owning pointer object, so that it'll point there. And then if you should, well, let's see, how far do I go with this example? So yeah, owning pointer is a class, and in its constructor, copy constructor, and assignment operator, it increments the reference count. So it makes sure that the reference count is updated every time a new thing points at it. Right? If you have a raw pointer, if you have a non-owning pointer that points to one of your classes, it will not increment the reference count. It didn't create new C++ magic. It just made so that we have a way to have smart pointers. So you have to use smart pointers all the time. Okay, so what happens if you've got your instance of your class and you now change the value of this? Oh, let me go back one. Sorry. The other thing that the owning pointer does is that it decrements the reference count in its destructor. So when an owning pointer goes out of scope, or if, say, it's contained in a class that's destroyed, its destructor gets called, and it will decrement the reference count for the object that you have. And so, yeah, and a little caveat here that I'm not going to go into. Okay, so let's say you change this owning pointer so that it's now 0. So you're going to change this pointer so it's now going to have the value null. Then what happens is it's going to decrement the reference count of the thing that it's pointing at. And then the thing itself is going to realize that it's been decremented, and it deletes itself. So it frees up that memory. Right? So you didn't call delete explicitly. And that's kind of the important part here. Is you also never call delete on a pointer that's pointed to by an owning pointer. There's one crucial exception to this, which is that if you have cycles in the ownership graph, I'll cover cycles in graphs in more detail tomorrow, then you can lead to problems. So this is that case spelled out where you've got the capability to point to another instance of yourself, and so you can construct, say, on the stack 2 pointers that point to each other, and that's the logic that would give you this kind of description set of pointers. And then if you set the values here to null, if you set the values to null, then they continue to point to each other. Their reference counts are both 1, and so they don't delete themselves, even though nothing can access this piece of memory. Right? In this way, you actually still have the capability for leaks. Java solves this in a different way with garbage collection. But like I said, there are issues with Java. Okay, so the solution to this problem is if you have to have, say, an object that needs to point back to the thing that owns it, is that you need the second class of pointers, which are access pointers, which are basically raw pointers, except they're in debug mode will tell you if you're trying to access a piece of data that's already been deallocated. They won't guarantee that the owning thing doesn't get deleted out from underneath you. Okay, so I'm going to bring this up because there's a good chance that we're going to be switching to another kind of owning pointer strategy. Previously, you had my class deriving from reference count, but that's annoying if you want to put like an integer or a standard vector into an owning pointer and have it shared between multiple classes, because you can't rederive integer from reference count. Integer is kind of its own thing. And so the solution to that is to have a separate location in memory where the reference count lives than from where the piece of data that you want to keep. And then you can put anything you want to into that smart pointer. And that's done with this boost shared pointer, and there are a lot of advantages of shared pointer. Except I'm still, and we haven't made this switch because there's like these stunning restrictions on how you initialize heap objects that I'm not so happy about. Yeah, that's the alternate picture. So instead of the reference count sort of living with the object, it lives next to it or somewhere else in memory. Okay, so so I want to say that if you create a new class and you derive it from reference count, then you want to create type defs for it and you put those type defs in what we call forward headers, where you say you declare the name of your class. Right? This just says this is a name for a class. It doesn't say anything about what that class does, and so it's a very simple thing to say, and the compiler is very happy to read those and process them quickly. And then you can say, these are the type defs that I want to have. So I can have an owning pointer to a residue type op, a residue type constant owning pointer, where the thing that's being pointed to is constant. We'll talk about constant on the third day, and using constant in C++. And then you can also have these APs, the access pointers as well, apps and caps. And so you can, yeah. So here's the use of it. The other thing that to say about this is that because you've declared these type defs in the namespace where your class lives, then the type def lives in that namespace, even though it's a type def to something in another namespace. So inside the core chemical namespace, you have a type def to something inside the utility pointer namespace, right? But this type def here lives in core chemical. So you talk about residue type cap, you would preface it by core chemical. All right, so I'm going to stop here, except that I'm sort of right on the cusp of talking about. It's actually no more slides, so I'm not cutting things very short. I'm not cutting things short at all. But this really cool concept of resource allocation is initialization, where you rely on constructors and destructors to secure and then to release resources. And so if you're ever working with classes that need to like lock down a piece of resource, say a location in memory or a block of memory, or like control of a printer, or maybe you have a mutex, you want to make sure that if you have two threads running, that only one of those threads has access to a piece of data at any point in time, and use a mutex to lock down that thing. Then constructors and destructors are the right way to go in terms of, or putting the logic to secure and release those resources in constructors and destructors is a really good design pattern. And so, yeah, I won't go into it anymore, except to say that I guess Matt's going to mention exceptions sometime later in the week, and talk about how when exceptions are thrown, they unwind the stack in such a way that they destroy, like they call the destructors for all the objects that are allocated on the stack. And so if you use a class that, say, allocates some memory on a heap, and you want to make sure that when an exception gets thrown, it doesn't leak memory, then if you use resource allocation as initialization, then you avoid that problem. I think that's it. Okay, sorry to go so long. We have, I think, I don't know, some cool looking desserts. I've got a light right in my eyes.
We're something behind schedule, but let's take a 5-minute, 10-minute break, just to stretch your legs and get some afternoon feet. And then we'll get back and we'll do a lab. I mean, like you had a. Oh, good. I guess I'm pushing.